We already know a little bit about random variables. What we're going to see in this video is that their random variables come in two varieties. You have discrete random variables, and you have continuous random variables. Continuous. And discrete random variables, these are essentially random variables that can take on distinct or separate values. And we'll give examples of that in a second. So that comes straight from the meaning of the word discrete. Distinct or separate values, while continuous, and there's just another definition for the word discrete, saying could be polite or not obnoxious, or that's not what we're talking about. We're not talking about random variables that are polite. We're talking about ones that are ones that can take on distinct values. And continuous random variables, they can take on any value in a range. And that range could even be infinite. So any value in an interval, So with those two definitions out of the way, let's look at some actual random variable definitions. And I want to think together about whether you would classify them as discrete or continuous random variables. So let's say that I have a random variable, capital X, and it is equal to, well, this is one that we covered in the last videos. One, if my fair coin is heads, it's a 0 if my fair coin is tails. So is this a discrete or a continuous random variable? Well, this random variable right over here can take on distinct values. It can take on either a 1 or it could take on a 0. Another way to think about it is you can count the number of different values it can take on. This is the first value it can take on. This is the second value that it can take on. So this is clearly a discrete. This is a discrete random variable. Discrete random variable. Let's think about another one. Let's define random variable y as equal to the mass of a random animal selected at the New Orleans Zoo, where I grew up, the Audubon Zoo, at the New Orleans Zoo, the Audubon Zoo. Y is the mass of a random animal selected at the New Orleans Zoo. Is this a discrete random variable or a continuous random variable? Well, the exact mass, and I should probably put that qualifier here, to make it really clear. The exact mass of a random animal or a random object in our universe, it can take on any of a whole set of values. I mean, who knows exactly the exact number of electrons that are part of that object right at that moment? Who knows the neutrons, the protons, the exact number of molecules in that object or part of that animal exactly that moment? So that mass, for example, at the zoo, it might take on a value anywhere between, well, maybe close to zero. There's no animal that has 0 mass, but it could be close to 0 if we're thinking about an ant, or we're thinking about a dust mite, or maybe if you consider even a bacterium an animal. I believe bacterium is a singular of bacteria. And it could go all the way, maybe the most massive animal in the zoo is the elephant of some kind. I don't know what it would be in kilograms, but it would be fairly large. So maybe you can get up all the way to 3,000 kilograms, or probably larger, say 5,000 kilograms. I don't know what the mass of a very heavy elephant, or a very massive elephant, I should say, actually is. I mean, something fun for you to look at. But any animal can have a mass anywhere in between here. It does not take on discrete values. You could have an animal that is exactly maybe 123.75921 kilograms. And even there, that actually might not be the exact mass. You might have to get even more precise, 10732. And I think you get the picture. Even though this is the way I define now, a finite interval, you can take on any value in between here. There are not discrete values. So this one is clearly clearly a continuous random variable. Continuous continuous random variable. Let's think about another one. Let's say that random variable y, instead of it being this, let's say it's the year that a random student in the class was born. Random student in the class was born. Is this a discrete or a continuous random variable? Well, that year, you literally can define it as a specific discrete year. It could be 1992, or it could be 1985, or it could be 2000 and 2001. There are discrete values that this random variable can actually take on. It won't be able to take on any value between, say, 2000 and 2001. It'll either be 2000, or it'll be 2001, or 2002. Once again, you can count the values it can take on. Most of the time that you're dealing with, as in the case right here, a discrete random variable, let me make it clear this one over here is also a discrete random variable. Most of the time that you're dealing with a discrete random variable, you're probably going to be dealing with a finite number of values, but it does not have to be a finite number of values. You can actually have an infinite potential number of values that it can take on, as long as the values are countable, as long as you can literally say, okay, this is the first value you can take on, the second, third, and you might be counting forever, but as long as you can literally list, it could be even an infinite list, but if you can list the values that it can take on, then you're dealing with a discrete random variable. Notice, in this scenario with the zoo, you could not list all of the possible masses. You could not even count them. You could, you might attempt to, and it's a fun exercise to try at least once to try to list all of the values this might take on. You might say, okay, maybe you can take on 0.01, maybe 0.02. Wait, you just skipped an infinite number of values that it could take on, because it could have taken on 0.011, 0.012. And even between those, there's an infinite number of values you can take on. There's no way for you to count the number of values that a continuous random variable can take on. There's no way for you to list them. With a discrete random variable, you can count the values. You can list the values. Let's do another example. Let's let random variable C, capital C, be the number of ants born tomorrow. Born tomorrow in the universe. In the universe. Now, you're probably arguing that there aren't ants on other planets, or maybe they're ant-like creatures. They're not going to be ants, but how do we know? So, number of ants born in the universe. Maybe some ants have figured out interstellar travel of some kind. So, the number of ants born tomorrow in the universe. That's my random variable C. Is this a discrete random variable or a continuous random variable? Well, once again, we can count the number of values this could take on. This could be 1, it could be 2, it could be 3, it could be 4, it could be 5 quadrillion ants, it could be 5 quadrillion 1. We can actually count the values. Those values are discrete. So once again, this right over here is a discrete. This right over here is a discrete random variable. This is fun, so let's keep doing more of these. Let's say that I have random variable, let's say random variable x. So we're not using this definition anymore. Now I'm going to define random variable x to be the winning time. Let me write it this way: the exact winning time. Exact winning time. Winning time for the men's 100 meter dash at the 2016 Olympics. 2016 Olympics. So the exact time that it took for the winner is probably going to be Usain Bolt, but it might not be, actually aging a little bit. But whatever the exact winning time for the men's 100 meter dash at the 2016 Olympics, and not the one that you necessarily see on the clock, the precise time that you would see at the men's 100 meter dash. Is this a discrete or continuous random variable? Well, the way I've defined it, and this one's a little bit tricky because you might say it's countable. You might say, well, it could either be 9.56 seconds, or 9.57 seconds, or 9.58 seconds. And you might be tempted to believe that because when you watch the 100 meter dash at the Olympics, they measure to the nearest hundredths. They round to the nearest hundredths. That's how precise their timing is. But I'm talking about the exact the exact winning time, the exact number of seconds it takes for that person to, from the starting gun, to cross the finish line. And there, it can take on any value. It can take on any value between, well, I guess they're limited by the speed of light, but it can take on any value you can imagine. You know, it might be anywhere between 5 seconds, and maybe 12 seconds. It could be anywhere in between there. It might not be 9.57. That might be what the clock says, but in reality, the exact winning time could be 9.571, or it could be 9.57235. 9. I think you see what I'm saying. The exact precise time could be any value in an interval. So this right over here is a continuous random variable. Now, what would be the case, instead of saying the exact winning time, if instead I define X to be the winning time of the men's 100-meter dash in the 2016 Olympics, rounded to the nearest hundredth. Is this a discrete or a continuous random variable? Delete this. I've changed the random variable now. Is this going to be a discrete or continuous random variable? Well, now we can actually count the actual values that this random variable can take on. It might be 9.56, it can be 9.57, it can be 9.58. We can actually list them. So in this case, when we round it to the nearest hundredths, we can actually list the values. We are now just dealing with a discrete random variable. Discrete random variable. Anyway, I'll let you go there. Hopefully this gives you a sense of the distinction between discrete and continuous random variables. Let's say we define the random variable capital X as the number of heads we get after 3 flips of a fair coin. So given that definition of a random variable, what we're going to try to do in this video is think about the probability distribution. So what's the probability of the different possible outcomes and the different possible values for this random variable? And we'll plot them to see how that distribution is spread out amongst those possible outcomes. So let's think about all of the different values that you could get when you flip a fair coin 3 times. So you could get all heads. You could get heads, tails. You could get heads, tails, heads. You could get heads, tails, tails. You could have tails, heads, head. You could have tails, head, tails. You could have tails, tails, heads. And then you could have all tails. So there's 8 equally, when you do the actual experiment, there's 8 equally likely outcomes here. But which of them, how would these relate to the value of this random variable? So let's think about what's the probability. There is a situation where you have 0 heads. So we could say, what's the probability that our random variable X is equal to 0? Well, this situation right over here where you have 0 heads. It is 1 out of the 8 equally likely outcomes. So that's going to be 1/8. What's the probability? What's the probability that our random variable capital X is equal to 1? Well, let's see. Which of these outcomes gets us exactly 1 head? We have this one right over here. We have that one right over there. We have this one right over there. I think that's all of them. So 3 out of the 8 equally likely outcomes get us to 1 head, which is the same thing as saying that our random variable equals 1. So this has a 3/8 probability. Now, what's the probability? I think you're getting at this point. What's the probability that our random variable X is going to be equal to 2? Well, for X to be equaling 2, that means we got 2 heads when we flip the coin 3 times. So that's this outcome meets that constraint. This outcome would get our random variable to be equal to 2. And this outcome would make our random variable equal to 2. This is 3 out of the 8 equally likely outcomes. So this is a 3/8 probability. And then finally, we could say, what is the probability that our random variable X is equal to 3? Well, how does our random variable X equal 3? Well, we would have to get 3 heads when we flip the coin. So there's only one out of the 8 equally likely outcomes that meets that constraint. So it's a 1/8 probability. So now we just have to think about how we plot this to really see how it's distributed. So let me draw. So over here on the vertical axis, this will be the probability, and it's going to be between 0 and 1. You can have a probability larger than 1. So just like this. So let's see if this is 1 right over here. And let's see, everything here looks like it's an eighths. So let's put everything in terms of eighths. So that's half. This is a fourth. That's a fourth. That's not quite a fourth. This is a fourth right over here. And then we can do it in terms of eighths. So that's a pretty good rough approximation. And then over here, we could have the outcomes. And so outcomes, I'll say outcomes for let's write this. So value for x. So x could be 0, 1. Actually, we do those same colors. X could be 0, x could be 1, x could be 2, x could be equal to 2, and x could be equal to 3. X could be equal to 3. These are the possible values for x. Now we're just going to plot the probability. The probability that x has a value of 0 is 1/8. I'll make a little bit of a bar right over here that goes up to 1/8. So I'm just going to draw it like this. So it goes up to, this is 1/8 right over here. The probability that x equals 1 is 3/8. So that's 2/8, 3/8 gets us right over that purple color. So probability of 1, that's 3/8. That's right over there. That's 3/8. So let me draw that bar. Just like that. The probability that x equals 2. Probability x equals 2 is also 3/8. So that's going to be that same level, just like that. And then the probability that x equals 3, well, that's 1/8. 1/8 is the same height as this thing right over here. So choose the wrong color. So it's going to look like this. It's going to look like this. And actually, let me just write this a little bit neater, and I can move that 3. So cut and paste. Move that 3 a little bit closer in, just so it looks a little bit neater, and I can move that 2 in actually as well. So cut and paste. So I can move that 2, and there you have it. We have made a probability distribution for the random variable x. And the random variable x can only take on these discrete values. It can't take on the value half or the value pi or anything like that. And so what we've just done here is we've just constructed a discrete probability distribution. Let me write that down. So this right over here is a discrete. The random variable only takes on discrete values. It can't take on any value in between these things. So discrete probability distribution. Let's define a random variable x as being equal to the number of heads. I'll just write capital H for short. The number of heads from flipping a fair coin. We're going to assume it's a fair coin. From flipping coin 5 times. And so like all random variables, this is taking particular outcomes and converting them into numbers. And this random variable, it can take on the value x equals 0, 1, 2, 3, 4, or 5. But what I want to do is figure out, well, what's the probability that this random variable takes on 0, 1, 2, 3, 4, and 5. And so to do that, first let's think about how many possible outcomes are there from flipping a fair coin 5 times. So let's think about this. So let's write possible outcomes. Possible outcomes from 5 flips. These aren't the possible outcomes for the random variable. This is literally the number of possible outcomes for flipping 25 times. For example, one possible outcome could be tails, heads, tails, heads, tails. Another possible outcome could be heads, 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 tails, tails. That is one of the equally likely outcomes. That's another one of the equally likely outcomes. How many of these are there? Well, for each flip, you have two possibilities. So let's write this down. So the first flip, there's two possibilities, times 2 for the second flip, times 2 for the third flip. Actually, not really, it's time limitation, like confuse the random variable. Two possibilities for the first flip, 2 possibilities for the second flip, 2 possibilities for the third flip, 2 possibilities for the fourth flip, and then 2 possibilities for the fifth flip, or 2 to the 5th equally likely possibilities from flipping a coin 5 times, which of course is equal to 32. And so this is going to be helpful because for each of the values that the random variable can take on, we just have to think about, well, how many of these equally likely possibilities would result in the random variable taking on that value? Let's just delve into it and see what we're actually talking about. All right, I'll do it light. I'll start to move. All right, so let's think about the probability that our random variable x is equal to 1. But actually, let's start with 0. Probability that a random variable x is equal to 0. So that would mean that you got no heads out of the 5 flips. Well, there's only one way, 1 out of the 32 equally likely possibilities that you get no heads. That's the one where you just get 5, where you get 5 tails. So this is just going to be equal to 1 out of the 32 equally likely possibilities. Now, for this case, they kind of think in terms of kind of the binomial coefficients, combinatorics, and all of that. It's much easier to just move through it, but just so we can think in those terms, and it'll be more useful as we go into higher values for our random variable. It's also, this is all the build-up for the binomial distribution, so we get a sense of where the name comes from. Let's write it in those terms. So this one right over here. One way to think about that in combinatorics is that you had 5 flips and you're choosing 0 of them to be heads. 5 flips, you're choosing 0 of them to be heads. And let's verify that 5 choose 0 is indeed 1. So 5 choose 0. 5 choose 0 is equal to 5 factorial over 5 minus 0 factorial over 0 factorial times 5 minus 0 factorial. 5 minus 0 factorial. Well, this is 0 factorial is 1 by definition. And so this is going to be 5 factorial over 5 factorial, which is going to be 1. Once again, I like reasoning through it instead of applying formula. But I just wanted to show that these two ideas are consistent. So let's keep going. I'm going to do x equals 1 all the way up to x equals 5. And if you are inspired, and I encourage you to be inspired, I try to fill out the whole thing. It's probably that x equals 1, 2, 3, 4, or 5. So let's go to the probability that x equals 2. I'm sorry, x equals 1. So the probability that x equals 1 is going to be equal to, well, how do you get one head? Well, it could be, the first one could be head, and then the rest of them are going to be tails. The second one could be head, and then the rest of them are going to be tails. I could write them all out. But you can see that there's just 5 different places to have that one head. So 5 out of the 32 equally likely outcomes involve one head. Write that down. So this is going to be equal to 5 out of 32 equally likely outcomes. Which of course is the same thing. This is going to be the same thing saying, look, I got 5 flips and I'm choosing one of them. I'm choosing one of them to be heads. That over 32. And you could verify that 5 factorial over 1 factorial times 5 minus, actually, let me just do it. So take my word for it. So 5 choose 1 is equal to 5 factorial over 1 factorial, which is just 1, times 5 minus 1 factorial, which is equal to 5 factorial over 4 factorial, which is just going to be equal to 5. All right, making good progress. So now let's, in purple, let's think about the probability that our random variable x is equal to 2. Well, this is going to be equal to, and now I have to resort to the common chords. So this is, you have 5 flips, and you're choosing 2 of them to be heads over 32 equally likely possibilities. This is the number of possibilities that result in two heads. 2 of the 5 flips have chosen to be heads. I guess you think of it that way by the random God. So whatever you want to say. And that's, so this is the fraction of the 32 equally likely possibilities. So this is the probability that x equals 2. Well, what's this going to be? Well, I'll do it right over here. Actually, no reason for me to have two colors. So 5 choose 2 is going to be equal to 5 factorial over 2 factorial times 5 minus 2 factorial. 5 minus 2 factorial. So this is 5 factorial over 2 factorial times 3 factorial. And this is going to be equal to 5 times 4 times 3 times 2. I could write times 1, but that doesn't really do anything for us. And then 2 factorial is just going to be 2. And then the 3 factorial is 3 times 2. I could write times 1. Once again, doesn't do anything for us. That cancels that. 4 divided by 2 is 2. 5 times 2 is 10. So this is equal to 10. This right over here is equal to 10 30 seconds. 10 30 seconds. And obviously, we can simplify this fraction. So I like to leave it this way. We're now thinking everything is in terms of 30 seconds. 1 30-second chance, x equals 0. 5 30-second chance that x equals 1. And 10 30-second chance that x equals 2. Let's keep on going. All right, I'll go orange. So what is the probability that our random variable x is equal to 3? Well, this is going to be 5 out of the 5 flips. We're going to need to choose 3 of them to be heads to figure out which of the possibilities involve exactly 3 heads. This is over 32 equally likely possibilities. And this is going to be equal to, so 5 choose 3 is equal to 5 factorial over 3 factorial times 5 minus 3 factorial. 5 minus 3 factorial is equal to 5 factorial over 3 factorial times 2 factorial. Times 2 factorial. Well, that's exactly what we have up here. We just swap 3 and 2. So this also is going to be equal to 10. This is also going to be equal to 10 30 seconds. All right, 2 more to go. And I think you're going to start seeing a little bit of symmetry here. 1, 5, 10, 10. Let's keep going. Let's keep going in white. The probability that a random variable x is equal to 4. Well, out of our 5 flips, we want to select 4 of them to be heads, or out of 5, 4. We want to see, we're obviously not actively selecting. What we think about it. We want to figure out the possibilities that involve out of the 5 flips. 4 of them are chosen to be heads, or 4 of them are heads. This is over 32 equally likely possibilities. So 5 choose 4 is equal to 5 factorial over 4 factorial times 5 minus 4 factorial, which is equal to, well, that's just going to be 5 factorial. This is going to be 1 factorial right here. So change the time. Is to multiply 1 factorial to 4 factorial. So it's 5 factorial over 4 factorial, which is equal to 5. So once again, this is 5 30 seconds. And you could have reasoned through this, because if you're saying you want 5 heads, that means you have 1 tail. And there's only 5, there's 5 different places you could put that 1 tail. There's 5 possibilities with 1 tail, 5 of the 32. And you could probably guess what we're going to get for x equals 5. Because having 5 heads means you have 0 tails, and there's only going to be 1 possibility out of the 32 with 0 tails, or we have all heads. Let's write that down. So the probability that our random variable x is equal to 5. So we have all 5 heads. And you could say this is 5, and we're choosing 5 of them to be heads out of the 32 equally likely possibilities. Well, 5 choose 5. That's going to be, let's right here, for all of the other ones. 5 choose 5 is 5 factorial over 5 factorial times 5 minus 5 factorial. Well, this right over here is 0 factorial, which is equal to 1. And so this whole thing simplifies to 1. So this is going to be 1 32nd. And so you see the symmetry, 1 32nd, 1 32nd, 5 32nd, 5 32nd, 10 32nd, 10 32nd. And that makes sense because the probability of getting 5 heads is the same as the probability of getting 0 tails. The probability of getting 0 tails should be the same as the probability of getting 0 heads. So I'll leave you there for this video. In the next video, we'll kind of graphically represent this and see. We'll see the probability distribution for this random variable. Let's say that you know your probability of making a free throw. You know the probability, let's say the probability of scoring, let's say make it miss, and then start that. So let's say the probability of scoring for a free throw is equal to, is going to be 7%. We want to write it as 1%, or we could write it as 0.7. We write it as and let's say the probability of missing the throw. This is just straight out of now. Probability of missing it's just going to be 100% minus this. You're either going to make or miss. You're either going to score or miss. I want to make it. We'll start with that. So this is going to be a 30% probability or 0.3. 1 minus 0.7. These are the only two possibilities, so they have to add up to 100%, or they have to add up to 1. Now let's say that you're going to take 6 attempts. And what we're curious about is the probability of exactly 2 scores in 6 attempts. In 6 attempts. So let's think about what that is. I encourage you, if you get inspired at any point in this video, you should pause it. You should kind of work through what we're asking right now. So this is what we want to figure out. Probably exactly 2 scores in 6 attempts. So let's think about the particular ways of getting 2 scores in 6 attempts. And think about the probability for any one of those particular ways. Then we can think about, well, how many ways can we get 2 scores in 6 attempts? So, for example, you could make the first 2 free throws, 4, and then you miss the next 4. So score, and it's miss, and miss. So what's the probability of this exact thing happening? Well, you have a 0.7 chance of making this of scoring on the first one. Then you have a 0.7 chance of scoring on the second one. And then you have a 0.3 chance of missing the next 4. So the probability of this exact circumstance is going to be what I'm writing down. Hopefully you don't get the multiplication symbols confused with decimals. I'm trying to write a little bit higher. Times 0.3. And what is this going to be equal to? Well, this is going to be equal to 0.7 squared times 0.3 times 0.3 to the 1, 2, 3, 4 to the 4th power. Now, is this the only way to get 2 scores in 6 attempts? No, there's many ways of getting 2 scores in 6 attempts. For example, maybe you miss the first attempt, and then you make the second attempt to score. Then you miss the third attempt, and then let's just say you make the 4th attempt, and then you miss the next 2. You miss and you miss. This is another way to get 2 scores. What's the probability of this happening? Well, as we'll see, it's going to be exactly this. It's just we're multiplying in a different order. This is going to be 0.3 times 0.7. 30% chance of missing the first one, 70% chance of making the second one, and then 0.3, 30% chance of missing the third, times a 70% chance of making the 4th, times a 30% chance for each of the next two misses. If you wanted this exact circumstance, this is once again going to be 0.7. If you just rearrange the word which you're multiplying, this is going to be 0.7 squared times 0.3 to the fourth power. So for any one of these particular ways to get exactly 2 scores and 6 attempts, the probability is going to be this. So the probability of getting exactly 2 scores and 6 attempts was going to be any one of these probabilities times the number of ways you can get 6 scores, times the number of ways you can get 2 scores in 6 attempts. Well, how if you have out of 6 attempts, you're choosing 2 of them to have scores, how many ways are there? Well, as you could imagine, this is a combinatorics problem. So you could write this as, let's see how I can, you're going to take 6 attempts. So write this as 6 choose, or we're kind of, you're picking from 6 things or 6 attempts, and you're picking two of them, or 2 of them are going to be need to be made if you want to meet these circumstances. So they're going to tell us the number of different ways you can make 2 scores in 6 attempts. And of course, we can write this in kind of the binomial coefficient notation. You can write this as 6 choose 2, 6 choose 2, and we can just apply the formula for combinations. And this looks completely unfamiliar. I encourage you to look up combinations on Khan Academy and go into some detail on the reasoning behind this formula. I think makes a lot of sense. This is going to be equal to 6 factorial over 2 factorial times 6 minus 2 factorial. 6 minus 2 factorial. 6 minus 2 factorial. What's this going to be? This is going to be equal to 6 times 5 times 4 times 3 times 2. I'll sort of the 1 there. I'll change the value over 2 times 1 over 2 times 1. And 6 minus 2 is 4, so that's going to be 4 factorial. So this right over here is 4 factorial. So times 4 times 3 times 2 times 1. Well, that is going to cancel. And then let's see, 6 divided by 2 is 3. So this is 15. There's 15 different ways that you could get, that you could pick 2 things out of 6, I guess is what you say it. Or there's 15, did I say 16? There's 15, then the 6 is 5. There's 15 different ways you can pick 2 things out of 6. Or another way of thinking about it is there's 15 different ways to make 2 out of 6 free throws. Now, the probability for each of those is this right over here. So the probability of exactly 2 scores in 6 attempts, this is where we observe a little bit of crumble. This is going to be 6 choose 2 times 0.7 squared. This is 2, you're going to make 2, and then 0.3 to the 0.3 to the 4th power. Notice these will necessarily add up to 6. So if this right over here was a 3, then this right over here would be a 3, and then this would be 6 minus 3, or 3 right over here. And now what is this value? Well, it's going to be equal to, we have our 15, 3 times 5. We have this right over here. It is 15 times, let's see, yellow, 0.7 times 0.7 is going to be times 0.49. Let's see, 3 to the 4th power would be 81. 3 to the 4th power would be 81, but I'm multiplying 4 decimals. Each of them have 1 space to the right of the decimal point. So I'm going to have, I'm going to have 4 spaces to the right of the decimal. So 0.0081. So there you go. Whatever this number is, we'll get a calculator out and calculate. So this is going to be, so it's 15 times 0.49 times 0.0081. 0.0081. And we get 0.59535. Two right now. I'll function a little bit more real estate. I'll write it in very bold color. This is going to be kind of out of bold colors. I'll write it in slightly less bold color. This is going to be equal to 0.05935 if we wanted the exact number. Or we could say this is approximately, if we round to the nearest percentage, this is approximately a 6% chance, 6% probability of getting exactly 2 scores in the 6th attempt. I didn't say 2 or more. I just said exactly 2 scores in the 6th attempt. And actually, it's a fairly low probability because I have a pretty high free throw percentage. If someone has this high of a free throw percentage, it's actually reasonably unlikely that they're only going to make 2 scores in the 6 attempts. Point on straight time, and you want to figure out the probabilities that 100 cars pass or 5 cars pass in a given hour. So a good place to start is just define a random variable that essentially represents what you care about. So it says here the number of cars that pass in some amount of time, say in an hour. And your goal is to figure out the probability distribution of this random variable. And then once you know the probability distribution, then you can figure out, what's the probability that 100 cars pass in an hour, or the probability that no cars pass in an hour. You'd be unstoppable. So, and just a little aside, just to move forward in this video, there's 2 assumptions we need to make because we're going to study the Poisson distribution. In order to study it, there's 2 assumptions we have to make. That any hour at this point on the street is no different than any other hour. We know that that's probably false. During rush hour in a real situation, you probably would have more cars than another rush hour. And if you want to be more realistic, maybe we do it in a day, right? Because in a day, any period of time, actually no, I shouldn't do a day. We have to assume that every hour is completely just like any other hour, and actually even within the hour, there's really no differentiation from one second to the other in terms of the probabilities that a car arrives. So that's a little bit of a simplifying assumption that might not truly apply to traffic, but I think we can make that assumption. And the other assumption we need to make is that if a bunch of cars pass in 1 hour, that doesn't mean that fewer cars will pass in the next. That in no way does the number of cars that pass in one period affect or correlate or somehow influence the number of cars that pass in the next. They're really independent. Given that, we can then at least try using the skills we have to model out some type of distribution. The first thing you do, and I'd recommend doing this for any distribution, is that maybe we can estimate the mean. Let's sit out on that curve and measure what this variable is over a bunch of hours and then average it up. And that's going to be a pretty good estimator for the actual mean of our population, or since it's a random variable, the expected value of this random variable. Let's say you do that and you get your best estimate of the expected value of this random variable is, I'll use the letter lambda. So this could be, 9 cars per hour. You sat out there, it could be 9.3 cars per hour. You sat out there over hundreds of hours, and you just counted the number of cars each hour. You average them all up. You say, on average, there are 9.3 cars per hour, and you feel that's a pretty good estimate. So that's what you have there. And let's see what we can do. We know the binomial distribution, right? The binomial distribution tells us that the expected value of a random variable is equal to the number of trials that random variable is kind of composed of, right? Before, in the previous videos, we were counting the number of heads in a coin toss. So this would be the number of coin tosses times the probability of success over each toss, right? This is what we did with the binomial distribution. So maybe we can model our traffic situation something similar. This is the number of cars that pass in an hour, right? So maybe we could say, lambda cars per hour is equal to, I don't know, let's make each experiment or each toss of the coin equal to whether a car passes in a given minute. So there's 60 minutes per hour. And then, so that there would be 60 trials. And then the probability that we have success in each of those trials, if we model this as a binomial distribution, would be lambda over 60 cars per minute. And this would be a probability. This would be n. and this would be the probability. If we said that this is a binomial distribution, and this probably wouldn't be that bad of an approximation if you actually then said, oh, this is a binomial distribution, so the probability that our random variable equals some given value k, the probability that exactly three cars pass in a given hour, would then be equal to n, so n would be 60, choose k, right, 3 cars, times the probability of success, so the probability that a car passes in any minute, so it would be lambda over 60 to the number of successes we need, so to the kth power, times the probability of no success, or that no cars pass, to the n minus k, right? If we have k successes, we have to have 60 minus k failures. There are 60 minus k minutes where no car pass. And this actually wouldn't be that bad of an approximation. You have 60 intervals and say this is a binomial distribution, and you probably get reasonable results. But there's a core issue here. In this model, where we model it as a binomial distribution, what happens if more than one car passes in an hour, right? Or more than one car passes in a minute? The way we have it right now, we call it a success if one car passes in a minute. And if you're kind of counting, it counts as one success, even if 5 cars pass in that minute. And so you say, oh, okay, so I know the solution there. I just have to get more granular. Instead of dividing it into minutes, why don't I divide it into seconds? So the probability that I have k successes, I'll do, instead of 60 intervals, I'll do 3,600 intervals. And so the probability of k successful seconds, so a second where a car is passing at that moment, out of 3,600 possible seconds, so that's 3,600 choose k, times the probability that a car passes in any given second. Well, that's the probability, that's the expected number of cars in an hour divided by the number of seconds in an hour. And we're going to have k successes, and then we're going to have, and these are the failures, probability of failure, you're going to have 3,600 minus k failures. And this would be even a better approximation. This actually would not be so bad, but still you have a situation where, 2 cars can come within a half a second of each other and say, oh, okay, so I see the pattern here. We just have to get more and more granular. We have to just make this number larger and larger and larger, and your intuition is correct. And if you do that, you'll end up getting the Poisson distribution. And this is really interesting because a lot of times people give you the formula for the Poisson distribution, and you can kind of just plug in the numbers and use it. But it's neat to know that it really is just the binomial distribution. And the binomial distribution really did come from kind of the common sense of, flipping coins. That's where everything is coming from. But before we kind of prove that this, if we take the limit as, we change colors. Before we prove that as we take the limit as this number right here, the number of intervals approaches infinity, that this becomes the Poisson distribution, I'm going to make sure we have a couple of mathematical tools in our belt. So the first is something that you're probably reasonably familiar with by now, but I just want to make sure. The limit as x approaches infinity of 1 plus a over x to the x power is equal to e to the a x, is equal to e to the a. And just to prove this to you, let's make a little substitution here. Let's say that n is equal to, let me say 1 over n is equal to a over x, and then what would be x would be equal to na, right? X times 1 is equal to n times a. And so the limit as x approaches infinity. As x approaches infinity, what does a approach? As x approaches infinity, what does n approach? Well, n is x divided by a, right? So n would also approach it. So this thing would be the same thing as making our substitution. The limit as n approaches infinity, 1 plus a over x, I mean the substitution is 1 over n. And x is, by this substitution, n times a. And this is going to be the same thing as the limit as n approaches infinity, of 1 plus 1 over n to the n, all of that, to the a. And since there's no n out here, we just take the limit of this and then take that to the a power. So that's going to be equal to the limit as n approaches infinity of 1 plus 1 over n to the n power, all of that to the a. And this is our definition, or one of the ways to get to E. If you watch the videos on compound interest and all of that, this is how we got to E. And if you try it on your calculator, just try larger and larger ends here, and you'll get E. So this is equal to, this inner part is equal to E. So, and we raise it to the A power, so it's equal to E to the A. So hopefully you're pretty satisfied. This limit is equal to E to the A. And then one other toolkit I want in our belt, and I'll probably actually do the proof in the next video. The other toolkit is to recognize that x factorial over x minus k factorial is equal to x times x minus 1 times x minus 2 all the way down to times x minus k plus 1. And we've done this a lot of times, but this is the most abstract we've ever written. And I can give you a couple of examples. And there'll be exactly, just so you know, there'll be exactly k terms here. 1, 2, 3, this one, first term, second term, third term, all the way. This is the kth term. And this is important to our derivation of the Poisson distribution. But just to make this in real numbers, you know, if I had 7 factorial over 7 minus 2 factorial, that's equal to 7 times 6 times 5 times 4 times 3 times 2 times 1 over 2 times, no, sorry, 7 minus 2 is 5. So it's over 5 times 4 times 3 times 2 times 1. These cancel out. You just have 7 times 6. And so it's 7. And then the last term is 7 minus 2 plus 1, which is 6. 7 minus 2 plus 1. And you had, in this example, k was 2, and you had exactly 2 terms. So once we know those two things, we're now ready to derive the Poisson distribution, and I'll do that in the next video. See you soon.
Any questions? It's complicated, right?
In this video, we're going to talk about how to use the Poisson distribution formula in order to solve problems. So take this problem, for example. A small business receives, on average, 12 customers per day. What is the probability that the business will receive exactly 8 customers in 1 day? So the first thing you want to keep in mind is that the time interval is the same. It doesn't change. So thus the mean is 12 customers per day, or the average. Now some textbooks will use lambda for the mean. I'm going to use this symbol here. Now to calculate the probability, we're going to use this formula. Capital X is the random variable. Lowercase x in this case is 8. That's the probability that we're trying to calculate. We want to know what's the probability that the business will receive exactly 8 customers in 1 day. So x is 8. And the formula is mu raised to the x e to the negative mu divided by x factorial. So let's replace lowercase x with 8. So this is going to be 12 raised to the 8 e to the negative 12 divided by 8 factorial. Now, keep in mind, e is the inverse of the natural log function, and e is basically a number. It's 2.71828. 8 factorial, that's 8 times 7 times 6 times 5, all the way to 1. So if you were to plug this into your calculator, you should get, hold on 1 second. You should get 0.065523, which if we multiply that by 100%, that's approximately 6.55%. So that's the probability that this business will receive exactly 8 customers in 1 day. Number 2, a student receives, on average, 7 text messages in a 2-hour period. What is the probability that the student will receive exactly 9 text messages in a 2-hour period? So what do you think we have to do in order to solve this problem? Go ahead and try it. Now, there's something that you need to pay attention to, and it's the time interval. Notice that the time interval, it doesn't change. It's the same. So therefore, 7 is the mean. Now, the only other thing that we need to find is x. We can clearly see that x is 9 because we're going to calculate the probability that the student will receive exactly 9 text messages in that 2-hour period. So we need to calculate P when x is 9. So let's go ahead and plug everything in. First, let's write the formula. So as we said before, it's mu raised to the x, e raised to the negative mu, divided by x factorial. So x is 9, mu is 7. So this is going to be 7 to the 9th power, e raised to the negative 7, divided by 9 factorial. So let's type that in. So you should get 0.1014, which correlates to approximately 10.14%. So that's the answer for part A. Now, let's move on to part B. First, let's get rid of this information. What is the probability that the student will receive exactly 24 text messages in an 8-hour period? So notice this time, the time period is different. So therefore, the mean is going to change. The mean was 7 when the time period was 2 hours. What is the new mean value when the time period is 8 hours? So by looking at these values, you can see what it is. To go from 2 to 8, you need to multiply the 2 by 4. So therefore, you need to multiply the mean by 4, which will give you 28. 7 times 4 is 28. So that's the new mean value. Now, sometimes the math will not work out as nicely as what we see here. So you can set up a proportion. If you want a formula to do this, you can use this one. Mu2 over mu1 is going to be T2 over T1. So we're trying to calculate mu2, which is, well, we're going to see that's 28. Mu1 is 7, T2 is 8, T1 is 2. So let's cross multiply. 7 times 8 is 56. And this is going to be 2 times mu2. Divide both sides by 2. We get 56 divided by 2, which is 28. Now let's rewrite what we know. So mu, we can see that it's 28, and x has to be 24. We want to calculate the probability that the student will receive exactly 24 text messages in this 8-hour period. So x is 24. So we're going to use this formula. P of x is equal to 24. That's going to be mu to the x. So that's 28 raised to the 24 power times e raised to the negative mu, which is 28 divided by x factorial. And so that's going to be 24 factorial. And this is going to be, the answer I got is 0.060095. So it's approximately 6%, or you could say 6.01%. So that's it for question 2 of this video. Number 3, a small business receives on average 8 calls per hour. What is the probability that the business will receive exactly 7 calls per hour? So we know how to do these types of problems. So we can clearly see that the mean is 8 and x is 7, since we want to calculate the probability when x is 7. So it's going to be P of x is equal to 7, and that's going to be mu to the x. Mu is 8, x is 7, times e raised to the negative mu over x factorial. So if we plug this in, this is going to be 0.1395865, or we could say approximately 13.96%. So that's the answer for part A. Now, let's move on to part B. What is the probability that the business will receive at most 5 calls in 1 hour? Now, mu is still 8. That's not going to change. But what is x? X could be any number, any whole number up to 5. So we want to find a probability that x is less than or equal to 5. So I'm just going to rewrite it here. So this is equal to the probability that x is equal to 0. Now, just to conserve space, I'm not going to write x all the time. But it's going to be plus the next one where x is equal to 1, plus when x is equal to 2, all the way to when x is equal to 5. So we have to add up the individual probability values. Now, fortunately, there's a quick way of doing this. I'm going to rewrite the formula to show you. So it's mu to the x, e to the negative mu, divided by x factorial. Now, x is the variable. U and e doesn't change. So what I'm going to do is I'm going to factor out e raised to the negative mu, and then write mu to the x over x factorial, because that's the part of the equation that's going to change with the change in x values. So we can say that p, when x is less than or equal to 5, is going to be e to the negative mu, which is e to the negative 8, and then times, we're going to plug in these values when x is 0. So mu is always 8, raised to 0 power over 0 factorial, plus, now when x is 1, mu is not going to change, it's still 8. The x is that.
What? Still searching YouTube for math help? Are the videos from 2006 real?
That mu value. And then when x is 2, and so forth. And then you could just follow the pattern. So this makes it a little easier to calculate the cumulative probability values. So go ahead and type this in your calculator. E to the 0 is 1. So I got 0.191236. So that's a 19.12% chance that the business is going to receive at most 5 calls in 1 hour. So that's it for part B. Now, let's move on to part C. What is the probability that the business will receive more than 6 calls in 1 hour? So the time interval is still 1 hour, which means mu is still 8. But now we want to calculate the probability that x is greater than 6, but not equal to 6. So x can be 7, 8, 9, 10, and so forth. Now this can go to infinity, so it doesn't end. How can we find the answer in this case? Well, let's draw a picture. The Poisson distribution has a graph that is decreasing over time. The probability is on the on the y-axis. The random variable x is on the x-axis or the horizontal axis. Now, let's say x is 6 at this point. So we're going to split the graph into 2 parts. Let me use a different color. Now, Now, let's say that the probability of the student receiving, let's say the probability that the business receiving 6 or less calls is 30%, just to give a number for the sake of illustration. What is the probability that X will be greater than 6? The total area under the curve, which represents the total probability, is 1 or 100%. So if the probability that X is equal to or less than 6, if it's 30%, then the probability that X is greater than 6 will be 70%, because these two have to add up to 100. So on the left side, this represents the probability that X is less than or equal to 6. On the right side, this represents the probability that X is greater than 6. Now, if we add these two values, this is going to equal 1. So if we take this term, move it to this side, we can say that the probability that X is greater than 6 is 1 minus the probability that X is less than or equal to 6. So this is going to equal 1 minus the probability that X is 0 plus the probability when X is 1 all the way up to 6. And I'm going to add a space. So this is going to be 1 minus, we're going to use the same procedure that we did in part B. So it's e to the negative 8, and then times mu to the x over x factorial. So mu is still 8, x is 0. And then plus 8 to the first power over 1 factorial, plus 8 to the second power over 2 factorial. And we're going to repeat this until we get to 6. So go ahead and type this in. Hopefully you have a scientific calculator, which will make life a lot easier when dealing with problems like this. So I got 0.6866626. So we can say that it's approximately a 68.7% chance that the business will receive more than 6 calls in 1 hour. So the chance is high. And it makes sense because the average is 8. So more than likely, it's going to receive more than 6 calls in an hour, if on average it receives 8 calls in an hour.
So if you answer this question correctly, you get like 20 points, okay? Anybody has an answer yet? Okay. Let's see. Just hold on to it, because we don't want to reveal the answer, obviously. You want to be the one who gets the 20 points. So like once we receive all the answers, kind of, we'll go in the order in which they were received. Okay? Of course, anybody who answers correctly is going to get their 20 points. It's not like the first one who came up with the answer. Okay? You guys like extra credit? It's fascinating that people from all over the world, right? Anybody else? Just raise your hand if you have an answer already. Give an answer, right? Yeah. Raise your hand if you do. Okay. 10 seconds remaining. Yeah. Well, I'll just show Homer grades to Nazi. Of course, if you bump back for that, then you bump on purpose, right? Because if you know, you're not right. Punish them for fun. And my wife, like, she's so persistent. She's I turn this on. Oh. Does anybody have an answer yet? I think they can't hear me. Tom, do you have an answer? Austin, do you have an answer?
Not yet. Almost there.
Yeah, do you have an answer? Hey, Mike is champion. You awesome. Can we go around? I'm just curious, like, where are you guys from? Like, just say your country. Is everybody here international? Okay, where are you from?
Germany.
From where?
Germany.
German. I was just asking her.
Oh, I'm from Denmark.
Denmark,
Yeah. I'm from
Colombia,
Russia.
Russia.
I'm yes.
Yes?
I'm the only not.
You're hiding like you see foreigners. India, Germany. So where are you from? Netherlands. Austria. What Austria?
Yeah.
Brazil. Germany. Belgium. England.
Germany.
Right? A lot of Germans. Cool. If you have an answer, you could just let me know. I'm just going to be waiting until you get an answer. I can see some smiles. You got the answer? Did you get an answer? There is no like credit punishment for like getting wrong answers.
You want to say it now or what?
No, not yet. Like I'm waiting to give folks a little more time. Just bear with me. Okay, so hold on to your answers. I'm going to ask a second question, okay? Can you hear me well? Do you all hear me? Okay, here's the second question. This is also 20 points, okay?
You notice the way I'm writing these questions that apply to actually real life business scenarios, right? But when you were learning, they were always applied to like coin flips and so forth, right? It didn't look like they were applicable to business, but they actually are. So anyhow, I mean,
So this is the second question. This is 20 points too. Can you see the question? Okay, 20 points. If you have questions, you can ask me questions too. So there's a second question. It's also 20 points. You have an answer? Sarah, right? Yes. Any answers?
No, we can't.
Not yet? Okay. You can ask questions if you need help. They have to be good questions. It's not like, can you answer this for me? Actually, no. Are you getting the answer from the video?
No, I was looking how you could do the
Formula?
on this calculator.
Oh, I see.
You know?
Oh, yeah, factorials. Yes. You can do them in Excel.
Yeah.
Yes. Question? Answer? Okay. Just hold on to it, please.
Can you answer both?
Yes. Eventually, yes. Any answers on this one? Yes. I see Don says yes. Anybody else? So why is an American in this class? Because you're a coach or something?
Yeah.
Okay. But no, you're an athlete, but like they're athletes too, right? So like, isn't this a class for international?
It's required for international, it's optional.
Oh, I see. I was just curious. So raise your hand if you already have an answer for this second one. I don't know.
Yes,
Oh my God.
I think we got it.
Okay, awesome.
Please approve.
Yeah, well done. Anybody besides Don get an answer? Okay. We'll be solving this as I sometimes bear with me. You know, on a piece of paper, write your answers and your name, your answer on a piece of paper for both questions. So like in this format. In this format. A name, first, second, describe the numeric answer. Actually, if you want, you can provide the formula too, because then that'll be partial set.
Do you want us to give you the paper?
No.
Or do you want us to
No, just hold on to it like, like I'll tell you, just do writing part right now. I'll tell you exactly what to do.
Okay.
Yes,
Have an answer to that second.
yes, like, did you hear what I just said? Like, write your name on a piece of paper. So write your answer to the first one and the second one. Don't forget to write your name, because if you don't write your name, how am I going to tell this it is? Or don't write your friend's name and write the wrong answer.
Can we write the same name in the same paper?
No, no, I'm just kidding. Like, you'll share the credit. It'll be like 20 splits.
Yeah.
10 points for that, or 5 points. Yeah, keep some of your points to that. Not so. If you can write your answers, don't show them yet. Write them on a piece of paper, and then you're going to hold them. Then I say hold them. Okay, not yet. Like just write them on a piece of paper and hold them. Not yet. Make them large enough so I can read them. Like not these large fonts. Sorry, it's kind of you have to keep the answers locked up for now because for obvious reasons. If you share your answer and you get caught, that's negative 20 points.
What?
Yeah. No, you do. I saw you work together. That's good. But if you're like, like doing nothing and then somebody comes and gives you the answer, and then you say, oh, I came up with the answer, you're not doing work, right? If you work together, you can split the credit. But if you think you can do it on your own, you might as well have your 20 points to yourself, right? Of course, this is 2 questions, 20 points. So if you answer both correctly, you have 40 points. Give a little box in the mistakes of my life was like updating on stats. It's doing fine. There's too much technology. People can text each other answers. I said, like, it's hard to keep the answers secret. Okay, so ready? Everybody? Shall I go ahead and solve that? Maybe another minute or 2? Okay. How many of you think like now that like you can get extra credit for like answering these questions, next time you're going to watch the videos more carefully? Raise your hand if you do. The fact that I give you credit will make you watch the videos more carefully. Raise your hand if you do.
I will watch it.
Thank you. Thank you, Christina, for being honest. Everybody's like, I was already watching it carefully. Hey, if if you have an answer, I might ask you how to do it on the board. Yeah, you were away, but you were saying if you have answers, write them on a piece of paper and hold on to it. Don't show it yet. Are we ready? If you're like off by let's say, I would say like if you're off by like 1 decimal place, it's okay. Actually, it depends on the probability. I'm not confused. I have to sit down and compute it. I'm going to show you how to do it both in Excel and how to do it by hand. Did you hear that, Maxwell? We're going to do it both in Excel and by hand. Being able to do it in Excel makes life really easy for large numbers and weird probabilities and so forth. Especially things that involve factorials. Yes. Okay, are we ready? Let's get going. Okay, so if you're ready, put your answers like in this row. Yeah, your name's on it, right? Yeah, it is. Yeah, just making sure. I'm looking out for you. Perfect. As long as the name's on, it's okay. You can talk to them. You don't have to. I mean, as long as your name is on it, it's not going to change itself, right? Are you guys ready? It's okay to be wrong. Like, it took humanity 2,300 years to get this right. It started in India, 6th century BC. It ended in Europe, I'll say 18th century or something. Okay? Thank God, India started the 6th century BC. I think it was a very long Are all the answers in? Like the lottery. Like the lottery, right? Yeah. Okay, thank you. I appreciate it. Is everybody ready? Okay. Actually, just hold on to your. I'm even if you show that they've thrown theirs in, so nothing's going to change. And you are all in different locations. So, okay. So, okay. So let's solve these, right? What do I say? Okay. So for the first one, right? It's a binomial probability problem. It's the same as flipping a coin. Yes. Is it dark? Yeah. Okay. I was afraid it's going to make like a camera stuff. So, now in here you have three parts. Okay. N is a parameter, P is a parameter. They don't change. X is a variable, right? It could change. For the binomial, X can go from 0 to N. So it could be 0, 1, 2, 3, 4, 5, depending on what N is, N minus 1 and N. Okay? In this case, let's write what they are. So it's saying, what is the probability? Let's start with N actually. N is 10, right? Because it's looking at 10 customers. You know, getting 10 customers is the same as flipping 10 coins, right? Like, you know, it's as though like there's this coin that is unfair. One side is more like, right? So in this case, the probability of success, the side you want to call it tails, you could call it heads, right? In this case, that side has written good customer on it. The other side is like bad customer. The bad customer side is like 60% of the time. Okay, the good customer side counts only 40% of the time. So, and P is equal to 0.4. That's the probability of success, getting a good customer in each trial. You know, you could think of this as like, I'm at a bank, customers are walking in, right? I know on average, they have like 40% chance of being like getting a loan from, right? Like it might be a mortgage, it might be something else. So they walk in, you know, they're either a good customer or a bad customer, right? But 40% of the time, they're good customers. That means 1 minus P, which is the probability of the failure, right? It's going to be 1 minus 0.4, which is 0.6. Okay? So let me actually write it here too, so that both sides can see it. So the first one is binomial. So, and I'm going to write it like kind of a little differently. So probability that large X is equal to little x is equal to combination n to the x. Normally, you'll write the x underneath it, like, you know. The way you write combinations is like this. Okay, since that is like math script, and I'm writing in Notepad made by Microsoft, you know, I can't do that. So I'm going to write it in this format. Engineers, you are probably used to like syntax and stuff, all kinds of programming, right? So P to the power X, does everybody follow? Like that hat means to the power. It's how many times I multiply P by itself, okay? And then I multiply that by, of course, I can put like stars in between for multiplication. So this is going to be 1 minus P to the power n minus x. Does everybody follow? Okay.
So that I can illustrate this a little better, I'm going to write some stuff here. Right. So in this case, this is going to be probability that x is equal to 5, right? Because I want exactly 5 customers. Little x is 5. Now, 10 to the 5, 0.4 to the 5, 1 minus 0.4 to the 10 minus 5. Hey, in between, I have got a question. And in the video, this was talked about. Here's a 10-point question. Why is there this first term? Why is there this combination term? Take your time. Don't answer it yet, but think through this like for a minute. I give you 10% credit if you answer that correctly. Why is there that combination term? Netherlands, like that's the best education system ever. No, that could be true actually. It's an amazing country. I just want to see hands like.
Are you asking why is there the 1 minus p term?
No, I'm asking actually the combination n to the x term, the very first term. Does everybody follow that? Why is there that term? See, like, okay, let me ask a few other questions. Those are also 10 points, okay? Like a little simpler maybe. Why is there p to the power x term? Why is there p to the power x term? Raise your hand if you can answer the simpler one. Like, why is there p to the power x term? Anybody? Okay. Now, the sad part is once you reveal the answer, the person hears. I guess you can write it on a piece of paper and show the paper or text it to me. You know, how many answers do we have here? 3? 4. Oh my God, goodness, good class. Okay. Okay. Sam, why do we have the p to the power x term?
No, I was gonna say the n.
Oh, okay. Hold on your answer then. Don't be done yet. Austin, my apologies. Can you write your answer on a piece of paper? Like real quick, simple. And you can make like simple mathematical notation. Don't show it yet. Can you guys also do it because there are multiple answers? I don't know. Because once one person says it, I'm denying the other people the opportunity to make credit. Okay? Yeah, absolutely. Absolutely. No. Actually, you know what? Let somebody, don't torture you. Oh, you know where it is? Oh, you know it? Okay. Okay. I was going to say, can you lend this gentleman some paper because it's like torture to find paper out. It's like, I don't know. Thank you, man. So the question is, the first question we're asking is, why is there p to the power x term? You know, like education systems worldwide are mostly based on memorization. Like, you know, there isn't much learning. It's always about doing, but not enough about learning. It's that kind of. You know, people use stuff without knowing why they work. Somebody has to know why things work. Helps you make new things, right? For once. Oh, you can hold on. It's either way. 6 of 100. Thank you. Yeah, you can read it. I trust you.
Do you want me to write the other one? Or
Yes, ma'am. Please.
Don't.
Oh, you mean like the first one, y n to the x?
Yeah.
Hold on to that. Not yet. Let's figure out why is there p to the x. P to the power x is 10.2. Okay, so not sure, like, how many of you have the answer to p to the power x? Austin, I know you said you have it, right? This is the first time. Of course, I did this in all my classes, but
I was thinking turning these into like a game. Like, but I don't know. Learning should be fun, right? You don't want to get bored. If you can learn mathematics, probability, statistics, having fun, that's a good thing, right? Especially if you learn. So how many of you are ready? 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 For both questions? How many of you are ready for both questions? Did you answer both questions? The first question was, why is there empty power extra? Yeah, you can write that too if you want. Yeah, go ahead. Help yourself. You only have to second. Yeah, good one. Okay, so the first one, like B asked B to the power x as the second question. But we're going to start with that, okay? So when I say like, so of course, in the order we asked, like we first asked this one, right? And ask this one. Here's the third question. You'll be out of here like in 10, 15 minutes. Don't worry. This is important. I want you to learn this. Here's the third question. Why is there a term P and a term 1 minus? That is 10 points. Sorry. Well, it's a good thing, right? Like a little exercise, a lot of points. By the time you're done, it's going to feel like you're done with your homework. You don't even have to take your homework. Or you can add it to it. Like, just if you bump it, it's like 100 points because you made like something like 67 points here. So, actually, did you hear that question? Why is there a P term? And why is there a P 1 minus P term? But why is there in that formula a P term? And why is there also a 1 minus P term? What should they stand for? Why are they in the formula? These are all related questions. Be a little more detailed, like, being precise. Here's a general question. Why do we use mathematics in science? There are two reasons we use mathematics. Why do we use mathematics like this? There are two main reasons we use mathematics in science to model processes.
Shorter than writing sentences.
That's excellent. That's one of them. It's concise, very shorthand. What is the other one? Actually, I'll give you 5% better percent. Say it again. Okay. Like it's related to what you said actually, but it's like a little, you have to tweak it a little. Yes.
Explain things like that because like mathematics is kind of everywhere.
Universal kind of, you can communicate well. Why can you communicate well? Why can't you communicate well with human language? Why don't they express things in words? Why do you write down formulas? You speak human language, right? This is like foreign. All of us. You spend a lot of time learning, right? It's precise. It's precise. Once you write something down in it, it's incorruptible. Okay, it means the same to everybody. Human language is very malleable. It means different things to different people. In context matters. Like if I tweak something a little bit, you might all start laughing at something. In another context, it might be sad. Okay? So, okay. Are you all ready? So, 3 questions. Take your time. Say it again. Yes, please. If you have all the answers, or as many as you can answer, yeah, please put them back. And make sure your names are on it. So what sports are in here? Soccer. Soccer and swimming. That's it? Wow. I had a swimming student in my class, undergraduate class. I did not know swimming is, you watch it, it looks simple. Swimming is the hardest sport, most demanding sport ever.
Yeah.
It could kill you, like, actually, if you're not careful with it. It's hard, right? Otherwise, many other sports always face that. It's like sprinting for the whole duration of the sport. Insanely hard. You don't realize that, right? You watch swimmers and you're like, they make it look easy. It's amazing. We can look at something and not realize how complicated it is forever. Human mind is very, doesn't understand complexity well.
Yeah, it's cheap.
Well, that cheap paper might get you 70 points or something.
I don't think so.
I hope I can read it. Well, if you can explain to me what it is, I'll give you your points.
I mean, I think you
Don't write it in code, like, like some, I don't know, like cryptic language or something.
know, like really wrote just
Morse code or something.
really
Okay. Okay. Like, let's spend another minute or two, get our answers in, and then we'll start. Okay? Those videos are awesome. The good thing about those videos are there on under modules. You can watch them as many times as you want. Okay? But sometimes somebody has to explain what is going on. You can like play with the formulas forever and not really realize what's going on. Okay? So these questions I ask are kind of trying to address that, but like filling in the blanks. And this is a graduate class, like you have to know what you're doing. It's sometimes easy to get points, but it's hard to understand things at a deeper level. So did everybody turn in their answers? Anybody else who's still writing? Okay. So how many swimmers? Swimmers, raise your hands.
Well, we're coaches.
Oh, it doesn't matter. You're
We're
swimmers.
swimmers.
Yeah. Well, to swim against students.
Yeah.
Yeah. I'm a student, but I learn everything.
Yeah.
And that was just a joke. So you two are coaches?
Yeah.
Okay, cool. Oh, that's fascinating. So everybody else is soccer? Ah, good soccer team. Fascinating.
use our best man.
That's like, wow. My hat off to you. So Christina, there's a women's soccer team too.
I am, yeah.
Okay. So, but like, that's like kind of from all over the place, right? Like people from different parts of the world are playing in it, right?
Yeah.
Do you have like Americans in it?
We do, yeah.
Okay. Soccer is kind of here like not the most popular sport. But,
We have 5 rivals.
okay. Ready? Everybody turn them in? Okay. Okay, so let's get going. And let's finish this up in the next 10 minutes. Okay. Now, you'll write your answer down for all the questions. What do you have? Need more time? No? Okay. So let's start with the first one, right? In the order of like, why is that an nx term? Now you can answer verbally. You already have your answer there. Yes.
Yeah, we have three here. There's like the number of ways and possibilities I can reach out.
You can arrange them. Yeah, exactly.
So to not write all of them because it's
You don't have to say anything else. I know exactly what you're saying. You have the correct answer. Yeah, those are the combinations, right? Like, let me give you an example.
Write it here so that they can see it too. For example, customers, right? I'm going to name the customers good, bad. Okay, just like coins, like, one side is good, it writes G, good customer, right? 40% probability. Probability is 0.4, 40% chances. The other side is bad customer, right? 0.6 probability. Okay, so for example, just by chance, right? 10 customers walked in, they could all be bad, right? So you could get like, of course, in this case, you're not interested in that, right? You want exactly 5 good customers, right? That means you exactly have 5 bad customers, okay? So I'm just going to give you a simple case. So good, 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 good. That is 5, right? Just by chance, the first 5 who walked in, they were all good customers, right? And the last 5 are bad, right? Am I interested in this? Does that fit like what I was interested in? It does, right? Because I want exactly, didn't you write? 5 with good credit, right? That's one of the cases. Okay? How many cases are altogether? Actually, this is last question. Okay? Please forgive me. How many cases are there altogether? You can answer that, that's 20 points.
How many what?
Cases. How many different scenarios are there?
5 or in general?
Like the first one. Let me help you. I flip a coin 3 times, right? Simpler question. Here I'm flipping the coin 10 times. And it's not a fair coin, right? I mean, if you have the answer, you have to write it.
oh, right now.
Yeah. Because this is 20 points too. Did you hear that, Natsu? How many times am I flipping the coin here? 3 times, right?
What's the question?
The question is like, how many different scenarios are there? Customer combinations are there? So for the first question, do you follow my question, Axel? Like I flip a coin here. It's like I'm flipping a coin 10 times, right? Like I have 10 customers. Each customer is like a coin. So one side is good customer, the other side is bad customer. But the good side is less likely, right? It's not a fair coin. Probability of the good side is 0.4, right? Now, to make your answer to the question simpler, right? This final question. If I flip that coin 3 times, right? How many different scenarios of coin sequences will I get? How many sequences will I get in 3 flips?
That question.
That's not the question. This is to help you to answer this question. Okay? Here, I'm doing 10 flips. So if you want to answer this one, this is yes. This is very important. Basically, this is like asking if I flip that coin 10 times, right? How many different sequences will I get of tails and heads? Right? Yeah, absolutely. If you answer the last one, then
I'm gonna put it here, so in case we have to get it.
doesn't matter. As long as your name is on. But if you want to separate the swimming team from the soccer people,
No, usually, but
So basically, I'm asking you this first question, like, how many different point loops are there when I look at point 10 times? Does everybody like understand that analogy? Like, like first question is just like coin flips. It's literally like one side of the coin, instead of being heads, tails, it's bad and good. But it's not fair, right? Most points are fair. Like weight distribution is the same. Like either side will come half the time. But here, the bad credit people are more likely. The bad side is more likely. It's heavier on that side. That equals more. Any questions, Axel? Everybody turn in their answers. I mean, you can take your time. Just have to ask for one. No pressure. Still want to answer. You can always wait it 1 more minute. How do you say God in Dutch? Hot? How do you say God in Dutch? Hot? Yeah. How do you say it? Say? You say it. Cold. How do you say it? Cold. See, I think some places they say it almost like K. A little bit. Some places.
He's from the south. And they
Okay, different. Good to know. You know which one is correct? I think the K is correct.
Mine is correct.
You know what? You know how we know it's correct? Because in Kurdish it's also hot. It's another Indo-European language. In German it's gold. In English it becomes softer God. T becomes D, Z becomes G.
His speech actually, it's officially a dialect.
Okay. Christina, how do you say Leiche in German? Like, in the south. Leiche, like a corpse. Like, how do you say?
Leiche?
Yeah, but that's northern pronunciation. How do you say it in the south? How do you pronounce it in the south, like Leiche? South German. Anybody from Bavaria? Nobody from Bavaria?
Ask the Austrians.
Ask Austrians, yeah. How do you say Leiche in your language? Same? Okay. I bet you there are German dialects that say Leiche. Just like ish. And the correct pronunciation is actually Leiche. Some dialects kept the original language. Because in Kurdish, you say Lashes. Okay, ready?
Yeah.
I should teach you like the probability of linguistics. Okay, ready? Everybody ready? Everybody turned it in? Okay. Let's answer the last question first. Okay? How many different sequences of good and bad customers are there? Yes, sir.
1,024.
Yes. Where is the past 24 raised? Answer past 24. Wow, fascinating. Who answered past 24? 2024? Okay. Remember like 3 Phillips? 1 Phillip, right? How many sequences are there? It's H and T, right? 2. 2 Phillips. H. What is it? Next one? HT, right? TH, TT, 4. Have you noticed? 2 to the power 1, 2. 2 to the power 2. This is the number of possibilities in each trial to the power number of possibility to the number of trials. Okay, so basically in this case, it'll be in each trial we have 2. It'll be 2 to the power n, and in this case, n is what? 10. So it'll be 2 to the power 10. If you are rolling a die, how many possibilities are there in each trial? 6. If you are rolling it 10 times, right? What will be the possibility number of sequences? 6 to the 10. 6 to the 10. Very large number. Okay? Okay, good. Very good. Did you hear that, Maxwell? So it's basically 2 to the 10. If it was a die, it'll be 6 to the 10. Okay, because at each trial there are 6 possibilities. If you do 2, there are 36. If you do it again, there are 216. 3 die rolls, possibilities. That's the number of sample space outcomes. Okay? So let's answer, why is there the NX term? And you answered that correctly. Why is there the NX term? Because that is showing you how many different ways you could squeeze in those 5 customers into 10 customers, right? It could be that the first 5 were good customers, last 5 were bad customers. But that is just 1 out of 1,024. It could be that the first one was good, but the second one was bad, but then there were like 4 in a row that were good, and the rest were bad. So you could put that like in different places, like it's almost like license plates. Okay? The license plate that has 10 letters, right? How many license plates can you make when 5 G's are on the license plate and 5 B's are on the license plate? Okay? That is n to the x. It's called combination n to the x. And of course, you already know the formula. The formula is n factorial divided by x factorial times n minus x factorial. Okay? Now, let's compute that. Oh, actually, before we do that, let's answer the other questions. Why is there the P term? Anybody? Anybody? What does P represent?
Successful tries.
Exactly, because there are successful trials, right? So, and probabilistically, if events are independent and you have X of them, you know, in each one of those cases, you're going to have a P for each. So, why is it P to X? Because that's the probability of getting 5 good customers, but ignoring their sequence changes. Okay? So, for example, let me ask you this. You know, actually, here's an example. You know, tell me 2 events that are independent. Being tall and being smart, they're independent. Right? There are smart, tall people. There are, I hate to say that. Actually, let me change it. You know, hair color, right? Blonde, brunette. So, is independent from height. Everybody agrees, right? Nothing to do with each other, right? So let's say the probability of being brown, oh, I think that might be. They're both bees. What percentage of people say it depends on which country you're from? Okay. Let's say the probability of brown is like 0.7, probability of blonde is 0.3. Okay, just for sake of argument, right? What is the likelihood that a person will have both? Actually, in this case, let me do it this way. Okay, the probability of, let me write it. The other was tall, right? Blonde and tall. How do you find that probability? How do you find the probability that somebody is both blonde and tall when those 2 events are independent? You know what you can do? That's the video of probability. You can just multiply the probability of blonde
by the probability of tall. Let me write that for Maxwell. Okay, so let me do like blonde and tall in case it's recording. Like I don't. Okay, so probability of brown and tall. Oh, I mean to put it there. Does everybody follow that? You can just multiply the probabilities. You know, I hope that I'm not recording. I'm going to give you an example. Somebody wants to get married. Okay? They're looking for certain qualities in their spouse, right? And let's say they have like 5 criteria. 5 criteria, right? They need to be smart. They need to be tall. They need to have brown hair. I don't know, blue eyes. And that's a smart I said. And they have to be German. Okay? So how would you find the probability? And all these things like look like they're independent, right? I mean, are there people with brown hair in Germany? It's kind of little related, right? You're more likely to find somebody who's blonde in North Germany, right? But let's assume like it's kind of like, you know, like Celts went there too. Okay? So, which they did actually, British Isles, now it turns out genetics is mostly Celtic, but phenotype you can't tell. So, how do you find the probability of finding those 5 traits? You know what you do? You multiply the probability of each one of them, right? So you want your spouse to be in the top 10% smart, top 10% tall, top 10% the other qualities. What is the probability of finding a spouse like that? Does everybody follow this? It is 1 over 10 to the power of 5. It is 1 over 10 to the power of 5, which is the same. It's 1 in 100,000 people. Do you think that's a really low probability scenario? You're doomed, right? They're looking for 1 in 100,000 people. And then you add like age, right? Because you're not going to marry somebody who's like 90 years old that has those policies, right? So there's probably more factors. So you have to like know probability to live in the world. Sometimes I see people actually asking for things they'll never get, like they don't even understand the process. Okay? Probability is everywhere. If you can think probabilistically, your life will be so easy. Okay? So, okay, let's answer. Why is it p to the power x? Because there are 5 good customers, right? And they're all independent. The first customer being good has nothing to do with the second customer, right? Of course, it will have to do with each other if they were spouses, for example. Because spouses like kind of support each other. If one is bad, the other is probably bad credit to you, right? Because they share income. But let's assume that's not the case. Like these are just separate people, like that you don't, it's per household or something. Okay? So that's why. Same here. Why is there a 1 minus p term? Because that's the probability of failure, right? And how many failures do you want? 5. That's why it's 1 minus p to the power of 5. Because the probability of getting 1 bad customer is 1 minus p. What is the probability of getting 2 bad customers? With the logic I just introduced you. This is called the law of independence. It is 1 minus p times 1 minus p. The probability of getting 3 bad customers, 1 minus p to the power of 3. Probability of getting 4 bad customers, 1 minus p to the power 4. Probability of getting 5 bad customers, 1 minus p to the power 5. Okay, why am I able to do this? Why do I multiply p's and 1 minus p together? Because these are independent within themselves. Good customers, one good customer has nothing to do with the other being good or bad. Okay, by assumption. You know, one customer being bad is not going to affect the other customer being bad, right? My credit is bad. It doesn't affect his good credit. Okay. Now, we talked about all that. And let's answer the questions themselves, right? Let's compute this. You see how powerful it is? You can apply it like, and there's like a gazillion different concepts in probability. You could apply them in ways, I hate to say this, it could make you billions. You know, and it happens. I could give you examples from the history of science where big money was made playing with formulas. Okay. So let's compute the first one. What is N? N is equal to 10. There are 10 customers. What is P? P is equal to 0.4. Now, actually, you can see that, right? What is
Yes.
X? How many successes do I need? 5. What does that mean? I automatically have 5 failures, right? Why is there that N minus X term? Because every failure is independent of the other, right? And how many do I need? N minus X. Okay, in this case, 10 minus 5 is 5 also. So let's compute this. So this is going to be 10 to the 5, okay, times 0.4 to the power 5 times 1 minus 0.4 to the power 10 minus 5. So it's basically equal to 10 to the 5 times 0.4 to the 5 times 0.6 to the 5. Okay, everybody follow that? Okay, let's open Excel, like instead of torturing ourselves. Actually, I can compute these like just by hand too. Let's do that. Okay. So 10 to the 5, right? Let's compute that first. So 10 to the power 5, that's 10 factorial divided by 5 factorial times 10 minus 5 factorial. So it's going to be 10 times 9 times, I don't know why I picked up such a lot of numbers. Times 5 factorial. 5 factorial times 5 factorial. 5 times 4 times 2 times 2 times 1. These two 5 factorials will cancel out. Did you see the trick I employed? I didn't write the rest of it down. I just left the 5 factorial. Why? Because I want to drag against the one at the bottom. Okay, get rid of it. Does everybody follow that? The trick. Okay. And then the rest is what? The rest is 0.4 to the 5, 0.6 to the 5. Okay, let's go to Excel. Does everybody follow? 252. That's the first part. Okay. And how do you do that in Excel? Use a function. Let me write the function. I'm just going to write it in the next cell. So you write like combine. Okay, once you write combine, it'll tell you like what the syntax is, right? It'll tell you like basically how many trials are there and how many are you choosing out of them. Okay, so it'll be like basically N and X. Okay. So in this case, of course, you have to write equals before it because it's a function. So let me write it into Notepad because Microsoft doesn't let you see functions themselves. So this first part, the first part is you write like equals combine 10, 5. That gives you 252. Okay. And then you can compute the next parts. So the next part is equals 0.4 to the power 5. Make sense? And the next part is 0.6 also to the power 5. Let's make this larger. And if you expand the cell, it'll give you more decimal places. Okay, however many you want to see. Now, what is left? We just have to multiply these three numbers, right? So you say equals A1, or you could write, there's a function called product. You could write actually these either inside it or write like from A1 to A3. Okay, you could do it either way. This is like the more lengthy way. If you have a lot of things to multiply, you use the product function. How many of you like have used Excel like a that's a bad question. Like when I say high level, like you could do like really advanced stuff, like even beyond regressions, like you could do simulations, all kinds of stuff. How many of you have used Excel like in statistics and probability before? Okay. That's the probability. Okay. Anybody who got this number? Raise your hand. You guys rock. Well done. Maxwell, was that? Yes, I can see the hands. Awesome. Well done. Okay, so let's answer the second one. Okay, we are asking. Now, if you look at the second question, it's a Poisson question. This is a Poisson question, right? The second one. You know, the average number of customers, let's go back to the question. Okay, you receive 10 customers, right, per hour. What does that mean? That is your number of successes per interval, right? That's the definition of the Poisson random variable. What is the difference between the Poisson random variable and the binomial random variable? How is X defined in binomial? How is X defined in Poisson? In binomial, X is number of successes, right? In Poisson, X is number of successes, but X is number of successes per interval. And that interval could be time, could be space per time, or time per space. Let me tell you what that means. I make string at a factory, right? I have 1,000 feet of string that I measure for quality control, right? On average, it has 5 defections, that's quality control, right? Actually, not on average, let's say it has 5 defections, which is lambda. But I need, let's say, if I have 6 or less, I accept it as pass. Does everybody follow? Even if it was one more than average, I still sell it. Okay? So did you realize it is, in that case, what is the interval? It's the length of string. It's not time. Okay, this is customers per hour. Right? Interval, like remember, like what does per mean? So this is like X is successes per interval. And that interval could be complicated. It could be interval per interval, like space per time, time per space. Let me give you one that has double units. I want to know the number of accidents from here to Knoxville, right? That is not a well-defined question. Why? Do you follow the question? If I want to know the number of accidents between here and Knoxville, right? Between Jefferson City and Knoxville, that's not a well-posed question. Why? Because that depends on
Unit time.
Exactly, that depends on time. That depends on time. By itself, it's not defined. Are you talking about a day? Are you talking about a month? That changes per time. So not only space matters in this case, right? Also time matters. If I extend the distance, right? Not to Knoxville, to Nashville, everything will change. My lambda will change, right? If I extend time from a day to a year, everything will change. Okay? So you have to have 2 units of interval in that case. In the case of the string, you only need 1 interval. What is the interval? The length of the string. You measure 1,000 feet, and that's what you're interested in. It's per length. In the case of the customer, what are you interested in? You're not interested in space, right? You're already assuming they're at Walmart. What are you interested in? You're interested in the span of time, because that's the only variable that determines how many customers are going to come to the cashier. Okay? So let's do this one. Let's do it first on the board, then we can do it on the sheet.
So what is lambda? In my question. Because lambda is the average number of successes per interval, right? Or per intervals, whatever it is. It is 10. Okay? How many successes do you want for that interval? 6. Okay, here's a question. What is the difference between x and lambda?
X is what you want, like in the future, and lambda is something that already passed in the past.
Okay. What's the difference? That's a very good answer, actually. You know, but like, is that an excellent answer? What is the average, right? The other is exactly how many at a given instance in time. Average, like she said, is taking over some many number of observations per time, right? How did you know like there are 10 customers per cashier at Walmart? You probably have data for the last 5-10 years. You computed an average, right? How do you get the average? You take the total number of customers, you divide by the total number of cashiers. And then you do that for hourly data. Okay? So, but in this case, did we say 5 or 6? 6. Okay, thank you. So let's compute it. So probability that x is equal to 6 is going to be 10 to the power. I need to erase this. 10 to the power 6, and then e to the power negative 10 divided by 6 factorial, x factorial. Now, what does it mean to take a constant or a variable to a negative power? What is e to the power negative 10? It's also equal to 1 over e to the power 10. Okay, I could have written this as 10 to the power 6 divided by 6 factorial times e to the power 10. Same thing. Okay, so the negative power means you can move that to the denominator as the positive power. Okay, so let's compute this in Excel. So there are 2 ways to compute this. You can do it manually, or you could use a function. Okay, so let's do it manually first. So, and let's do it in 3 steps, right? Like each part, let's compute it, right? So the first part is what? Lambda to the power x, right? In this case, it's what? 10 to the power 6? Is that right? 10 to the power 6. You know how you take powers in Excel? You put the hat. You put like 10 hat 6. Okay, that's like basically a million in this case. Okay. The next one. In the denominator. What do we have? 6 factorial, right? How do you take factorials in Excel? Factorials are really horrible, right? They're like, they get large fast, especially if the number is large, right? If you have like 100 factorial, you're doomed, right? So you can write like fact, okay? And then in parentheses, you can write what the number is. In this case, what am I doing? I'm interested in 6 factorial. Of course, 6 is a simple number, right? It's just 720. It's not a large number. You could have done it in your head, right? And what is the last one? E to the 10, right? And don't forget, if you take it as e to the negative 10, you have to put it in the numerator. If you take it e to the power 10, it's in the denominator. Depends on how you want to use the formula. I could have written this formula. Instead of like that. I could have written it as lambda to the power x divided by x factorial times e to the power lambda. I didn't need to know like what does negative powers mean. Okay. So the last part is e to the power 10. Now, how do you make e in? Now, you have 2 options here. You can either memorize, you could memorize like 2.71, 828, or you could actually have Excel compute or approximate e to like probably 15, 20 decimal places. How do you do that? Let's do that. You write exp
exp, and then open up parentheses, whatever power you want, you put it inside it. If I just put 1, right, it's going to give me e. Do you remember, like, from the videos? Maxwell, are you following? Like, the stuff I'm doing in Excel? So I'm like, so how do I write, for example, if somebody asks me, show me how to compute E in Excel, right? What do you need to do? You write equals in an empty cell, and then write exp in parentheses, you write 1. Because that's e to the power 1. Okay, the power is inside the parentheses. Any number to the power 1 is the number itself. Because the power is how many times you're multiplying the number by itself, right? So, but in this case, I'm not interested in e, right? What am I interested in? I'm interested in e to the power 10. I'm not going to put 1. I'm going to put 10. I have to multiply e by itself 10 times. Really large number, right? So remember, what was our formula? First number in the numerator, the other 2 multiplied goes to the denominator, right? So in an empty cell, I go here, I write equals, right? And what is my first number? It's going to be D1, because in D1, I have the numerator. Okay, so it's going to be D1 divided by, and open like a parentheses. There's order of precedence. It depends on the software. It's not software. I mean, it's human written. Like, you know, they have a protocol. Like, Excel sometimes does things that a statistician or a programmist, like somebody trained, like wouldn't do their way. Okay, like sometimes they diverge from the normal. So it's good to avoid like risky stuff. So this will be D2 minus D3. Okay. How many of you got that probability? 0.06. Okay. 0.06. Okay. Did you see that, Maxwell? How many of you got it, Maxwell? Awesome. Well done. Well done. Okay. Now, I'm going to show you how to do this with functions instead of like torturing yourself with the like different parts of the numerator, denominator, or like in the binomial case, like many different parts, the factorials. Remember, like this was what we were interested in, right? In the binomial case. So all you have to do is write binom, right? And the nice thing about Excel is like if you write the name of the function, like binomial, if you start typing binomial, it'll show you the functions list. See here, you can use this one, okay? Binomial, dot this. So I write like binom this. And the nice thing is once you open it, it tells you what the syntax is. In the parentheses, it is saying number S. What is that? That's number of successes. Okay, number of successes. So in this case, how many successes do I want? In my question, how many successes did I want? 5, right? It was like 5 out of 10, right? So I put 5. What's the number of trials? 10, right? What is the probability of success? 0.4, right? The last one is saying, is it cumulative? It is not cumulative. You know what cumulative means? Add up all the probabilities to that number of successes, right? Let me show you what that means. That's very confusing. If I write probability x equals 5, let me write it here actually. We're almost done, like we'll be gone like in 5 minutes. If I write probability x equals 5, okay, that is an individual probability. But if I write probability x less than or equal to 5, okay, that is the probability that x equals 0, or x equals 1, or x equals 2. Or x equals 3, or x equals 4, or x equals 5. Okay? Now, the good thing is binomial probabilities are mutually exclusive. Okay? Like remember 1024 cases, none of them can happen at the same time. You cannot get 3 successes and 4 successes at the same time. Then those events cannot happen together. When that happens, you can just add the probabilities. Okay, you can have the probabilities. So this probability is equal to probability x equals 0 plus probability x equals 1 plus dot, dot, dot. I'm going to use dot, dot, dot. You know what I'm doing, right? I'm using like 3, 4. And then I'm going to write the last one. Probability x equals 5. So now you know what cumulative means, right? You add up all the probabilities up to that number of successes, all the ones before it are added to it. For example, for 5 successes, we're looking at the probability of 0 success, 1 success, 2 success, 3 success, 4 success, 5 successes. In this case, are we looking at the sum of those? No, we're just looking at 5 itself. So the last number in the Excel formula, if you go back, what are you going to put in there? You're going to put 0 or false. You could write false. You know, it shouldn't accept either one. Does everybody see it's the same number? Let me make it larger. What does that tell us? It's correct. Okay, that's a check. You could do it by hand, then check in Excel, then check it through an Excel function. Let's do the Poisson. Remember, what's the probability? 0.06, right? So you know what we do? We write P Poisson, right? Distribution. And then I open the parentheses, right? It says X. What is X? X is number of successes per interval. In this case, how many successes do I want? I want 6 customers at that cashier, right? So number of successes is 6. And then what is the mean? On average, how many do I get? On average, I get 10. Is it cumulative? Do I want like 6, 5, 4, 3, 2, 1, 0, all those together? No. I just want exactly 6. I'm not talking about 6 or less customers, right? I'm talking about exactly 6 customers. So I put 0 again. Magic, it's the same number. Okay? Now, just bear with me. Now is the time to earn your hard-earned points. Okay, I need volunteers. Since we're not wearing masks, we're going to take the risk. And if you get COVID, don't hold it against me. Because if there's COVID, it's already got. So somebody is going to read these answers against mine. And if they're correct, just read me the answers. I'll decide if they're correct. And then I'm going to write down points. Okay? Not so. How many of your answers were correct? Like, let's start with Don. Don, you don't have to answer that. You can send that to me in an email. If you don't want to show your answers, it's totally fine. I don't. It's all up to you. Yes, sir. I'm listening. Your mic is muted. Yes. It's all up to you. Like, you can just send them to me in an email. Okay? Max will send them to me in an email. I trust you. Okay? Okay, so let's get started.
You want to read it from there?
Yeah, somebody needs to read it for me.
Okay,
Swimming coach and parade.
all of them.
Yes, ma'am, please.
Okay.
Thank you, I appreciate you.
We're gonna
Hold
read
on.
it. Lucky one.
Hold on. I gotta go right now. Just hold on. Hold on, let me stop share. Okay. This concludes the tonight's class. That's it. You all have a good night. Okay, now, so
Good night.
good seeing you. Take care. Okay, bye-bye. I'll look forward to seeing you next week. We can have our after-class chat. I'll hold you like another 15 minutes after that. Have a good night.
Have a good night. See ya.
Good night. Bye.